Okay, so picture this. You've got this hyper-competitive world of medical AI, specifically cancer diagnosis, what the field calls computational pathology, or CPAth.
Right. And in this world, you have these huge multi-million-dollar corporations, and they are locked in what is basically an intellectual arms race.
An arms race, exactly.
Right.
And their whole strategy, their entire bet, is on just brute force. They're training these absolutely colossal AI models on just astronomical amounts of data.
And we're not exaggerating the numbers here. I mean, we have competitors on the record saying they've used 3.1 million slide images, WSIs.
3.1 million. These are the heavyweights, the Virtuo 2s of the world.
Yeah.
They've really defined the entire game by saying that scale and only scale is how you get to state-of-the-art performance.
The thinking was you have to see everything to understand anything. To accurately interpret this incredibly complex visual data of human tissue, you just need more and more and more of it.
Exactly. The prevailing wisdom has been you need the biggest data lake, the most powerful compute cluster, and that's it. Then, almost out of nowhere, a new model, well, a new set of models, comes onto the scene. And it fundamentally rejects that whole scale only rule.
And this is where it gets really interesting.
One of these models, called OpenMidnight, achieved performance that was comparable to, and in some key cases, actually superior to those titans.
Yeah.
But it was trained on just 12,000 publicly available slides.
Just 12,000.
And here's a number, the one that just changes the entire conversation. The estimated cost to train it, $1,600.
That financial gap, I mean, $1,600 versus the millions, maybe tens of millions, that the industry leaders are spending. It's not just an economic difference.
No.
It's a fundamental, paradigm-shifting challenge to the entire philosophy of computational pathology. It's basically proof that really clever, elegant algorithmic design can absolutely trump brute force data.
And this isn't some fluke. It's not like they just overfit to one data set.
Yeah.
This is sophisticated, algorithmic genius proving that quality and efficiency can conquer this idea of just massive, uncurated quantity. So today, that's what we're doing. We're taking a deep dive into the technical breakthroughs that powered this revolution. We're looking at the original Midnight models from a company called Kaiko.ai, and then the replication, and really the critical improvement, OpenMidnight from Sofont.
And our mission for this deep dive is a full technical analysis. We want to know how they did this. How was this radical data efficiency actually achieved? We're going to unpack the specific, sometimes subtle, but highly technical changes to the standard AI training pipeline that let them just bypass this idea that foundation models must improve with scale.
We're getting into the math, the data prep,
Yeah.
the little architectural shortcuts that made all the difference.
Yeah.
So settle in. If you want to know what this means for the future economics of medical AI and how small teams, academic labs, can now credibly compete with these huge multinational giants, you have absolutely come to the right place. All right, let's start by maybe defining the domain a little more clearly. Computational pathology, CPath. For anyone who's maybe new to this specific field, we're dealing with images that are, well, they're fundamentally different from anything you'd see on, say, Instagram.
Not even in the same universe. CPath is all about applying deep learning to these digitized whole slide images. And these aren't your standard JPEGs. These are massive multi-gigapixel scans of tissue biopsies.
Usually stained with something called H&E, right? Hematoxylin and eosin.
That's the one. And the final file, the WSI, is huge. It can be several gigabytes for a single slide. It contains this just overwhelming amount of visual information.
So the AI's job is what, exactly? To help the human pathologist.
Exactly, to assist with these really high-stakes tasks. Things like finding tiny clusters of tumor cells that a human might miss after looking at hundreds of slides, or grading the severity of a cancer, segmenting out specific cell types for analysis.
And it can even do things you wouldn't expect, like predicting non-visual features.
That's where it gets really powerful, predicting things like gene expression profiles or even a patient's survival risk, purely from the visual patterns in the tissue. The morphology.
In the foundation model, the FM is sort of the core engine that makes all of that possible. It's not the final diagnosis tool itself.
No, it's the generalization engine. The FM's whole goal is to generate these very informative, very general representations of the image. We call them embeddings.
Embedding.
I think of the embedding as the model's own highly condensed, structured summary of what that piece of tissue looks like. And once you have that really high-quality summary, you can then adapt those embeddings very, very cheaply for all those different downstream tasks you mentioned.
How cheaply?
Usually with something as simple as a linear probe or just a tiny amount of fine-tuning, the heavy lifting is already done by the foundation model.
But you can't just feed a multi-gigabyte image into a model all at once. The hardware can't handle it.
Correct. And that's a crucial point. That's why these FMs in pathology are almost always tile-level FMs. You have to break that massive WSI down into smaller, manageable patches or tiles.
Usually something like 256 by 256 pixels.
That's a very common size. And the model learns from those individual tiles. This approach is key because it lets the model learn both the really fine local cellular details and, by looking at many tiles, the broader tissue context.
Okay, so that brings us back to that philosophy we started with. Scale is king. Why did the entire industry come to believe that they needed millions and millions of these slides?
Well, in their defense, the complexity of the problem seemed to demand it. Pathology images are just. They're notoriously messy.
Messy how?
You have immense heterogeneity, variations in patient demographics, how the tissue was prepared, how thick it was sliced. The staining protocols are different from lab to lab. Even the scanner that digitizes the slide can introduce artifacts.
So the industry's logic was to build a model that's robust enough to handle all those variations.
It needed to see practically every variation possible. The only way to do that, they thought, was with a data set of unprecedented scale.
And acquiring that data is, it's frankly a terrifying prospect.
Yep.
Our sources lay out the scale of the big players that Midnight and OpenMidnight were up against.
The numbers really are staggering, and they tell a story about the economic and logistical moats that were built around this field.
Let's hear them.
Okay, so you have WSI-2. This model kind of set the benchmark for scale. It was trained on 3.1 million WSIs.
3.1 million.
And just think about the costs of that. It's not just the GPUs. It's data governance, petabytes of storage, anonymization, securing data rights from hospitals all over the world.
A massive undertaking.
Then you have UNI-2, trained on data from over 350,000 WSIs. And H-Optimus-0, trained on 500,000. These were not small academic projects. These were major, multi-million-dollar corporate investments.
All based on this one core belief. That the sheer complexity of pathology required what was essentially an unbounded data resource.
And this is precisely what makes the Midnight philosophy so revolutionary. Kaiko.ai, the team behind it, they just asked this really fundamental strategic question.
Which was?
Are we hitting diminishing returns on scale? Is it actually crucial to have a data set that massive? Or could we get similar, maybe even better results with way fewer slides just by being smarter about the algorithm?
They shifted the focus from resource gathering to algorithmic refinement.
Exactly. From aggregation to optimization. And I love the analogy in their model names. Midnight.
Right. Named after the bathypelagic zone of the ocean, the deep midnight zone.
Yeah, it's this great parallel between model depth and scale and the zones of the ocean. Their first big success was with Midnight 12K, trained on just 12,000 slides.
And not from some secret proprietary data set.
No, from the publicly available TCGA dataset, the Cancer Genome Atlas. This is a tiny, tiny fraction of what the competitors were using. And what's incredible is that even this minimal data model performed comparably to WSI-2.
Which had, 258 times more data?
Something like that. It's an insane difference. Then they scaled up a little bit to Midnight 92K by adding a proprietary set of 80,000 slides just to see how their smarter algorithms would perform with a modest data increase.
And that then brings us to OpenMidnight by Sophon. And this wasn't just another model in the series, it was a replication study.
A replication study that, in many ways, was even more important than the original.
Why?
Because it confirmed the hypothesis and dropped the barrier to entry even lower. Sophon took the original Midnight 12K pipeline, the one that used only the 12,000 public TCGA slides, and they set out to reproduce the results while making their own small pipeline efficiencies.
And the result was OpenMidnight.
Which not only proved that the low data approach was real and repeatable, but it actually achieved the highest average performance among all the models in their comparison, a score of 0.775.
And critically, they did it for that unbelievable cost, just $1,600.
That successful replication is really the nail in the coffin for the scale-only rule. It proves this amazing performance isn't hidden behind a giant proprietary data wall.
It's achievable with public data, and just really, really smart engineering.
It just accelerates the entire field. The OpenMidnight team was able to use 16 times fewer GPU hours and finish their training in a quarter of the time it took for the original Midnight 12K.
Wow.
The core insight here, for you listening, is that the competitive edge in CPath is shifting so rapidly. It's moving away from who has the most data to who has the most refined algorithm and the smartest training strategy.
Okay, let's peel back that curtain then. Let's get into the core technical recipe. How do you actually pull off this kind of efficiency miracle? It has to start with the fundamental architecture.
It does. And for both Midnight and OpenMidnight, the foundation is the Vision Transformer, or VIT, architecture.
Which is pretty standard these days for big vision models. They've largely replaced the older convolutional neural networks.
Right, but the key here is the sheer size of the model they managed to use effectively on such a small data set. They used the VIT G14. The G stands for giant. This model has 1.1 billion parameters.
A billion parameters. I mean, for context, that is a truly colossal network.
It is. They use a smaller one, the VIT B14, which has about 86 million parameters for some of their ablation studies. But the final top-performing models are the giants.
But that seems completely counterintuitive. Training a billion parameter model should require, I don't know, a nearly infinite amount of data to stop it from just catastrophically overfitting.
It should.
If you show a model that big, only 12,000 slides, shouldn't it just memorize them immediately and then be totally useless on any new data it sees? Why did this massive model work so well here?
That paradox is, well, it's resolved entirely by how they initialized it and how they trained it. The whole training framework is built on DINOv2.
DINOv2.
It's a really powerful self-distillation framework that comes from earlier work on Dino and iBot.
Let's unpack DINOv2 a bit, because it sounds like it's the real engine for the self-supervised learning part of this.
Absolutely. Self-supervised learning is the trick that lets the model learn without any human-provided labels. You don't need a pathologist to circle every single tumor. And DINOv2 is particularly sophisticated.
How does it work?
It runs on a self-distillation principle, so it teaches the model to produce consistent representations, those embeddings we talked about, for different augmented views of the same image tile.
So you take one little patch of a pathology slide, and you show the model a zoomed-in version and a rotated version, one where you've changed the colors a bit.
Exactly. And the model's job is to learn that all of those different views are fundamentally the same piece of tissue. It has to distill its own knowledge.
And why is DINOv2 such a good fit for pathology data? I mean, compared to maybe older methods like contrastive learning.
Because pathology is inherently multi-scale, and it's incredibly textured. DINOv2 is specifically designed to learn both the global context, so the overall arrangement of the tissue, where the boundaries are, and the fine-grained local structure.
The shape of individual cell nuclei, that sort of thing.
Precisely. The specific shapes of nuclei or cellular infiltration patterns. By demanding that the model produce consistent embeddings across all those different augmentations, DINOv2 forces its 1.1 billion parameters to encode these really robust location-invariant and highly detailed features of the H&E image.
Which is critical, because the tiniest morphological difference can be what separates a benign condition from a high-grade tumor.
That's it. So you need a model that can see both the forest and the trees. DINOv2 is good at that.
Okay, now we get to what you call the cheat code, the single biggest efficiency step. The reason this cost $1.06 a.m. Pre-trained checkpoints.
This is the economic game changer. There's no other way to put it. The OpenMidnight team, specifically, started their training process not from scratch, but with a pre-trained 1.1 billion parameter VTG DINOv2 checkpoint.
And this checkpoint, it wasn't pre-trained on other medical images.
Yeah, and this is so important. It was a checkpoint that was previously trained on natural images, things like ImageNet. Cats, dogs, cars, landscapes, not a single pathology image in sight, as per the original DINOv2 release.
So they didn't start their giant model from a blank slate. They started with a brain that already understood the basic principles of vision.
That's the perfect analogy. If you think of the VTG as this giant, powerful calculator, starting from scratch is like first having to teach the calculator what the number 1 is and what a plus sign means.
It was unbelievably expensive.
Especially for a billion parameter model. The first, 80% of your multi-million-dollar compute budget and months of training time is just spent learning the absolute fundamentals of vision. Edges, corners, textures, basic color separation, the physics of light. The model is effectively learning what makes a thing a thing.
But by starting with that VITG checkpoint that was trained on natural images, the model already has all of that fundamental visual intelligence baked in.
That's right. To use your analogy, it's like handing that powerful calculator to a new employee who already has a PhD in physics.
Okay.
That employee doesn't need basic training. They just need a very minimal, highly specific orientation to adapt their existing knowledge to the specialized domain of pathology. The model only needs to spend its, 667 GPU hours adapting that general visual knowledge?
Learning the specific texture of chromatin, the particular pinks and purples of H&E stains, the morphology of cancer cells?
Yes. But hang on, you might ask, if you take a model that's an expert on cats and dogs and then suddenly force it to look at human pathology, isn't there a risk of catastrophic forgetting?
Right. Wouldn't the model just forget all its general knowledge as it tries to specialize so quickly?
That's an excellent question, and it really highlights why the DINOv2 framework is so successful here. Because DINOv2 forces the model to maintain these robust, generalized embeddings, the adaptation process is less about replacing knowledge and more about refining the existing feature space.
So the basic building blocks of vision edges, textures, are still incredibly useful for looking at tissue.
They are, and the key is that they only ran this transfer training for a very short duration, just 250,000 steps. That's likely just enough to gently bias the existing features towards the histology domain without causing this catastrophic erasure of the general vision knowledge.
So you're not wiping the slate clean, you're just
Right.
adding a new layer of expertise.
You're transforming a generalized VIT into a specialized, high-performance CPath feature extractor. And you're doing it by leveraging the massive initial investment that the DINOv2 researchers already made. You're effectively getting millions of dollars of pre-training for free.
So that pre-trained checkpoint is the accelerator.
Yeah.
But even with that huge head start, 12,000 slides is still a tiny sample size for a model this big, which means the quality of every single piece of data you show it has to be perfect.
As close to perfect as you can get. This is where the meticulous data preparation and filtering process comes in. This is where the quality over quantity strategy really comes to life.
Let's start with the data source itself. It's the TCGA dataset.
The Cancer Genome Atlas, publicly available, 12,000 slides covering 32 different cancer types. This is the cornerstone. The fact that this data is public is what enabled the $1.6K model.
Did they try adding more data?
Kaiko.ai did. They later explored scaling up with a proprietary set called NKI80K. But what's really telling is that their own studies showed that adding other public data sets like GTEx or CPTAC, it didn't really bring substantial improvements.
So just adding more data for the sake of it wasn't the answer.
No. The method of extraction and, more importantly, filtering was the key.
Okay, so let's get into the mechanics of that. Tile extraction. They're breaking these giant WSIs into 256 by 256 pixel tiles.
Correct. And they're sampling them at multiple magnifications, so 2x, 1x, 0.5x, and 0.25 YMPX. This is to make sure the model is exposed to various resolutions at the same time.
Now, how they actually generated the patches, the methodology, that varied a little bit, right?
It did, and it's an important engineering detail. The original Kaiko.ai team used something called online patching.
Online patching.
It means the WSI is streamed from storage, and the tiles are generated and sampled on the fly directly during the training loop. The main advantage is that it saves a ton of space.
Because you're not pre-calculating and storing every possible tile.
Exactly. If you were to do that, which is called offline patching, for 12,000 WSIs, you would need petabytes of storage. It's just not feasible for most labs. Online patching has a much smaller storage footprint.
And what does SoFont do for OpenMidnight?
They used a variation of offline patching. They pre-computed the patches but still used random sampling with overlaps during the training. But both approaches really prioritize this dynamic, non-rigid sampling to maximize the diversity of the tiles the model actually sees.
All right, now for the filters. The first one is about maximizing relevance, the foreground threshold.
Simple, but absolutely crucial. They put in a minimum 40% foreground area threshold.
So if a sampled tile is mostly just white background.
Less than 40% actual tissue, it gets thrown out immediately. This just stops the model from wasting precious compute cycles learning how to identify empty space.
But the real elegance, I think, is in the next step. Filtering out tissue that is foreground, but is, lunk information, like big swaths of fat, adipose tissue. This is the HSV color filter.
This is a really sophisticated domain-specific filter. The goal here is to maximize the, let's call it the biological entropy of the tile. You want regions that are dense with nuclei and cellular activity. That usually means epithelial tissue or active tumor areas.
And fat tissue or low-density stromal tissue, it looks very different under an H&E stain.
Very different, often washed out, pale, clear of dense color.
So the filter uses the hue, saturation, and value components of the color space to find and discard those regions. Can you walk us through the logic of those specific number ranges?
Sure. A tile is only accepted if at least 60% of its pixels fall within these specific color criteria. So in H&E staining,
First hue, 90, 180.
this range is key. It's designed to capture the colors of the actual stains. Hematoxylin stains cell nuclei a bluish purple, which has a high hue value. Eosin stains the cytoplasm and other tissues pink or red, which has a lower hue. This range effectively targets the colors common to dense, properly stained biological structures and filters out weird, off-color artifacts.
Okay, next saturation, 8, 255.
This one is about making sure the tissue isn't washed out. Adipose tissue, or necrotic dying tissue, often has very, very low color saturation. They set a low minimum threshold of 8 just to make sure the tile has some actual color depth and isn't just, a blurry, faded patch.
And finally, value or brightness, 103, 255.
Right. This helps get rid of artifacts or maybe extremely dark, overstained regions. But more importantly, it's great at separating the densely stained tissue from unstained or very lightly stained areas like fat, which typically fall outside that brightness range.
So by chaining all these filters together, the original 12,000 slides are transformed. Every single tile that the 1.1 billion parameter model sees is now guaranteed to be biologically relevant, high quality, and structurally dense.
You're maximizing the learning potential of every single GPU hour.
Absolutely. And they paired this filtering with HED color augmentations.
Working in the hematoxylin eosin DIB color space. Right. And this is to handle the inevitable variability in staining that you see from different labs. It's a way of artificially creating the diversity that, 3 million slides might provide naturally. It's synthetic diversity.
And it's another area where Sofont made a small but important tweak.
They did. They found the original augmentations were a bit too aggressive and actually decreased their strength for OpenMidnight, which turned out to be another little optimization that helped training.
Okay. We've covered the architecture and the data. Now let's talk about what might be the single most critical algorithmic switch they made, the KDE regularizer. If data quality maximizes the information content, this regularizer maximizes the stability of the learning process itself.
This is where the core mathematical innovation really is, and it's not a trivial change. The standard DINOv2 framework uses something called the Kaleo loss, or regularizer. Kaiko.ai and Sofont completely replaced it with the kernel density estimation, or KDE, regularizer.
Why do they have to do that? I mean, what happens if you try to train a giant 1.1 billion parameter model on a tiny 12,000 slide dataset using the standard DINOv2 setup?
The biggest risk is something called model collapse, or mode collapse.
Okay, good say.
When you have this massive capacity, 1.1 billion parameters, and a very limited number of unique samples, the model finds it incredibly easy to converge to a trivial, non-diverse solution. Imagine the model just decides, okay, all cancer looks like this one specific texture, and it stops learning anything else.
So the standard regularizer, the Kaleo loss, wasn't strong enough to prevent that from happening in this specific situation.
Exactly. It tries to spread the embeddings out, but it wasn't sufficient to prevent this deep instability in what we call the low data, high capacity regime.
So the KDE regularizer steps in as a stronger force for stability. And diversity, how does it actually work, mathematically speaking?
It imposes a soft constraint on the embedding space. It uses the mathematical properties of kernel density estimation to make sure that the distribution of all the generated tile embeddings stays diverse and well spread out in that high-dimensional feature space.
It's actively looking for clumps.
That's a great way to put it. It measures how dense the embeddings are in certain areas, and it actively penalizes the model if it starts clustering too many different input tiles into the same few output embeddings.
It's like an internal mathematical police force, preventing redundancy. It forces the model to actually use all of its 1.1 billion parameters effectively by requiring every tile, even very similar ones, to generate a unique and highly informative vector.
Exactly. You're forcing the model to retain feature diversity, and that is the absolute cornerstone of its ability to generalize to new data later on. And we know this swap was necessary because of the ablation studies.
What do they find?
Kaiko.ai reported unequivocally that without the precise combination of the KDE regularizer and the HSV color filter, the training for their smaller models simply did not converge.
It just failed.
It failed. They had instability, mode collapse, and they couldn't produce a usable feature extractor. So it's this combination of meticulous data quality and strict mathematical stability that is the core algorithmic innovation that finally truly dismantled the scale-only rule.
The technical elegance is just. It's undeniable, but the result that will make everyone sit up is the cost. We really have to dissect the economics here, because this is the data point that democratizes the entire field. How does OpenMidnight get to SOTA results for $1.06K when its competitors are spending millions?
It's a really stunning financial efficiency, and it was achieved by minimizing the single most expensive variable in any AI training run, GPU hours. So let's look closely at the specs that Sofont provided for the OpenMidnight training. This is the $1.06K model trained on the 12,000 public slides.
Let's walk through that $1.06K calculation in detail.
Okay, Sofont used 8 NVIDIA H100 GPUs. These are the fastest, most efficient accelerators you can get today. Each one has 80 gigs of memory. They ran a total batch size of 384 tiles at a time across all those GPUs.
And the total training process?
Capped at 250,000 steps, or iterations. The total wall clock time for this was remarkably short, 83.33 hours.
Less than 4 days. Continuous training, but less than 4 days.
Correct. So you multiply that wall clock time by the number of GPUs. 83.33 hours times 8 GPUs gets you a total of 667 GPU hours.
667.
Sofont then used a conservative estimate for the market rate of a cutting-edge H100 GPU hour, which is about $2.50. You multiply 667 hours by $2.50.
And you get $1,667.50.
Precisely.
Let's just pause on that. $1,600. That's the price of a decent laptop. It's not supposed to be the price of a state-of-the-art medical foundation model that's going to help diagnose cancer. This is revolutionary.
And now compare that to the original, which was already considered data efficient, the Midnight 12K model by Kaiko.ai. Even their optimized model, because it didn't use that pre-trained checkpoint shortcut.
It was much more expensive.
Much more. It required 32 NVIDIA H100s, and it ran for a full 1 million iterations. Their total training time was 14 days, or 336 wall clock hours. That calculates out to over 10,700 total GPU hours.
So OpenMidnight used 16 times fewer GPU hours, 667 versus over 10,000, and it finished in a quarter of the time. It's optimization layered on top of optimization.
Right. And the economic analysis really shows you the 3 layers that got them this massive cost reduction.
Okay, layer 1.
Transfer learning leverage. Starting with that pre-trained 1.1 billion parameter checkpoint, that just eliminated the entire expensive initial phase of learning basic vision, saving thousands of GPU hours right off the bat.
Layer 2.
Reduced iteration count. Because the data was so high quality and the training was so stable because of the KDE regularizer, OpenMidnight reached convergence and SOTA results in just 250,000 steps. That's a quarter of the 1 million steps the original design needed.
And layer 3.
The high-quality data pipeline itself. That HSV filter ensured that every single one of those 250,000 steps was spent learning high-value biological information. It maximized the value of their very limited compute budget.
This cost profile just fundamentally changes the political economy of CPath research. Before, only the giants with massive budgets could even play this game.
And now, the barrier to entry has shifted from a multi-million-dollar corporate budget to something that any well-funded university lab or even a small, lean startup can manage. It democratizes the ability to train your own foundational feature extractor.
It must accelerate innovation because it lets these smaller teams spend their limited resources on novel algorithm development or clinical validation, not just trying to replicate these expensive data collection efforts.
That's precisely why Sofont highlighted the difference. They proved that algorithmic efficiency, paired with smart architectural choices, makes the pure scale approach look economically redundant for achieving SOTA feature extraction.
The story of efficiency is incredible, but the final test is always performance. I mean, did the $1.06K model actually stand up to the multi-million-dollar competition?
It did. The benchmarks are pretty definitive on this. When they evaluated it against the standard evaluation suite, which is called EVA, and the gene expression benchmark HEST, OpenMidnight achieved the highest average performance score of 0.775 among all the models they looked at.
So that confirms it. Data scale is not the sole determinant of success.
Not at all. And it's not just the average. They had specific, really notable wins. OpenMidnight set new state-of-the-art scores on the Breakin's breast cancer classification task and the CAM16 lymph node metastasis detection task.
And even the original Midnight 12K model, their starting point.
Even that one performed comparably to Virtuo2, the 3.1 million WSI behemoth.
So the entire Midnight philosophy is validated. Targeted, clever algorithmic design can equal, or in some cases, outperform brute force data scaling. But the Kaiko.ai team, they didn't stop there. They explored an advanced technique to refine their embeddings even further.
Right, especially for tasks that require really fine-grained spatial accuracy. They called it high-resolution post-training.
This is a deep dive into fine-tuning strategy now.
It is. They took their slightly larger Midnight 92K model, and they dedicated a substantial amount of compute just to fine-tuning it for an extra 120,000 iterations. The goal was to enhance the embedding quality specifically for segmentation tasks, which need pixel-level precision.
But how do you get a high-resolution advantage if the vision transformer architecture itself is fixed?
You manipulate the input. During this fine-tuning stage, they increase the size of the training tiles from the standard 256 by 2576 pixels up to 512 by 512. Now, the critical insight is how a VIT processes data. It breaks the input image into these discrete patches or tokens.
Okay.
When you feed it a larger 512 by 512 image, the model generates significantly more of these patch tokens for the exact same physical region of tissue compared to a 256 by 2576 input.
So you're essentially feeding the model twice the amount of immediate visual context. You're forcing it to learn higher frequency, more granular details about the cellular structure.
Exactly that. You're boosting the resolution of the model's internal representation without having to change the BiTG architecture itself. And the resulting model, which they called Midnight 92 K392, it achieved the absolute best average performance in Kaiko.ai's own evaluation. And it showed these really striking improvements on nucleus and cell segmentation tasks.
So for tasks that need to see the tiny details, it worked beautifully.
Beautifully. But this specialized high-resolution training, it wasn't a silver bullet, it wasn't a panacea, and it came at a significant cost bump.
It required a lot more compute.
A massive compute scale-up for that phase, 48 GPUs. But more importantly, the source notes this crucial trade-off. This high-resolution procedure actually degraded the performance on certain other tasks, specifically the Chameleon-16 classification task and the HEST gene prediction task.
Wait, why would improving spatial detail hurt something like gene prediction? That seems counterintuitive.
Right. It's a fascinating nuance, isn't it? Tasks like gene expression prediction or general classification often rely more on global context and these sort of low-frequency morphological patterns, the overall architecture of the tumor and its microenvironment.
Not the pixel-perfect boundary of a single nucleus.
Right. By optimizing the model to focus so intensely on those high-frequency details from the 512 by 512 patches, they may have accidentally diluted the model's ability to extract those crucial low-frequency contextual cues. It's a great reminder that optimization is still highly task-dependent in pathology.
Which brings us to this really crucial meta point that the SOFONT authors raised. The success of these data-efficient models, it kind of exposes some serious flaws in how we're even evaluating these things. They call the current situation a messy performance landscape.
The variability is just too high. The very fact that a single model can't dominate all the tasks suggests that the benchmarks themselves might be poor proxies for truly generalized feature extraction.
And they had an even more alarming warning sign.
They did. This is the real red flag. Vision transformer models trained only on natural images, like a base DINOv2 model trained strictly on ImageNet that has never once seen a pathology slide, can sometimes outperform these highly specialized CPath foundation models on specific pathology tasks.
So a model trained on pictures of flowers and cars can beat a dedicated pathology model on a pathology task.
On certain tasks, yes, like HEST.
That means the benchmark isn't measuring clinically relevant pathology features. It's just measuring some generalized visual property that DINOv2 is inherently good at learning from any image.
Exactly. The success of OpenMidnight is really a siren call for better governance in CPath benchmarking. The field needs to stop chasing these marginal, tiny improvements on these generalized proxy metrics and start building better curated, more rigorous benchmarks that actually align with real-world clinical utility.
What a pathologist actually needs.
What a pathologist actually needs. Not just high accuracy on a toy dataset, but robustness across different staining conditions, and the ability to predict molecular features that will actually inform a treatment decision. The OpenMidnight paper is effectively arguing for a shift in focus, away from just scaling up models and towards building better, more clinically relevant evaluation.
This deep dive has really showcased an incredible inflection point in medical AI. I mean, the journey from multi-million-dollar budgets staked on massive proprietary data walls to a $1 6K state-of-the-art model is just a masterclass in meticulous engineering and strategic algorithmic design.
The key takeaway is so clear. The radical data efficiency of OpenMidnight and Midnight was achieved through a specific and, most importantly, a replicable technical recipe.
Let's recap that recipe one last time.
It includes starting with a massive pre-trained DINOv2 checkpoint to just bypass those initial high compute costs,
Yeah.
employing meticulous data filtering with the HSV color filter and foreground checks to maximize the quality of every single WSI tile, and critically, using the KDE regularizer to ensure training stability and the diversity of the embeddings, which prevents model collapse when you're in that low data, high capacity regime.
And by open sourcing the Midnight 12K weights and releasing the full training pipeline, Sofont and Kaiko,
Yeah.
AI have lowered the barrier to entry to a degree that is, frankly, unprecedented.
They've accelerated research and ensured that students, small academic teams, researchers all over the world, can now genuinely participate in developing the next generation of CPath models. You no longer need institutional access to petabytes of proprietary data.
This shift just empowers creativity. The competitive focus is now firmly on who has the most novel algorithm, the superior training strategy, not just who has the biggest bank account.
That's right.
Which leaves us with this final, provocative thought for you to consider. If foundation models trained on 12,000 public slides can match or even beat those trained on millions of proprietary slides, does the true competitive edge in medical AI now shift entirely away from data accumulation and towards algorithmic novelty and the critical evaluation of actual clinical utility?
And what happens when these incredibly data-efficient methods are applied not just to the current DINOv2 architecture, but to the next generation? Architectures like DINOv3, which may be even more efficient at transfer learning.
That is the technological and the economic question that will define how we move forward in computational pathology.
And the answer is now accessible to almost anyone.